you can go. Okay, perfect. So I think I will start. So good morning, everybody. I'm Alessandro, and I'll give you a presentation on tracking on GPU with LHCb full trigger software. And so, okay, let me start with a brief slide on the LHCb detector upgrade. So the goal is with the major upgrade to record 15 advanced femtobarns in run 3, increasing the luminosity by a factor 5, so reaching 2 to 10 to the 33. We're going to have an upgrade of most sub-detectors and readout system, but I don't want to go into too many details. I would prefer to talk about the trigger and the trigger upgrade. So here the idea is to remove the hardware trigger. And why do we want to remove it? So I want to point you to this plot, which shows the trigger yield versus luminosity. So this is the actual run 1-2 luminosity, so 4, 10 to the 32. And so as I said, for run 3, we're going to have 10 to the 33. So it's not in this plot, it's far on the right. And here you can see some typical LHCb decays of interest. So what we see here, for example, on green is a decay with muons in the final state, and these decays here are decays with hadrons in the final state. So what we clearly see here is that we were already saturating with the trigger at run 2, when we're running run 2 with this luminosity. So if you can imagine, we extrapolate this line to 10 to the 33, we're fully saturated. So in practice, we don't gain anything by increasing the luminosity. So the idea is to remove the hardware trigger and do everything software. But okay, to do this, we need to do the full reconstruction of events at 40 megahertz of LHC. And this will have an increase on the hadronic channels triggering efficiency by a factor 2 to 4 with respect to run 2. And so to show you then how the trigger changes between run 2 and run 3. So in run 2, we have the 40 megahertz bench crossing rate going into the L0 hardware trigger, which reduces it from 40 to 1 megahertz. And then we go into the software trigger. And here the difference, what happens in run 3 is that, okay, we still have the 40 megahertz bunch crossing rate, and we go directly to the software high level trigger. And I want to show you how the LHCb data flow works, showing this plot that we saw also yesterday, actually. So we have the LHCb bunch crossing at 40 megahertz. Actually, 30 megahertz are non-empty PP collisions. We have a full detector readout, and then we go into our software trigger, which is divided into HLT1, which is fully on GPU. And we saw a talk, the very first talk was by Tom, and then we'll see also today a talk by Bridge. We'll talk about tracking in HLT1. And then we have a buffer, and we have some time to do alignment and calibration. And here we're going to have a talk by Florian later today, and we go into HLT2, which is on CPU. We do a full detector reconstruction and selection, and we saw many talks yesterday, by Andre, Isaac, and Seta. But okay, my talk is focused on HLT1 and on GPUs. So why using GPU? To explain you this, I need to show you how we take data in LHCb. So we have raw detectors info that are sent to our custom data processing center, which are actually FPGA cards that receive data at 32 terabits per second. And then we have what we call event builder, which are in practice CPU servers that get this info and produce event packets. And in the EB servers, we have slots for GPUs, up to 3 GPUs per EB servers. So this is in practice with 0 overhead cost adding GPUs here. So this is one reason. And then most of the HLT1 tasks are highly parallelizable, as we know, like for tracking. And then to convince you even more about the GPUs, I want to introduce the Allen project, which is the project that handles HLT1 at LHCb. And I want to show you this plot, which shows the Allen throughput versus theoretical 32-bit T-flops. In practice, this represents the performance of a GPU. And so what we see is that if we have more performant GPUs, the Allen throughput scales linearly. So in practice, if in the future we have higher luminosity, this can be handled just by have improved the GPU technology, and no saturation is expected. So this is very promising also for the future. But okay, I talked about GPUs. Now let's dive into the topic, which is tracking. So HLT1 performs full upfront charge particle reconstruction down to a momentum threshold of 3 GeV. And for LHCb physics purposes, different type of structs we need to reconstruct. So to show you our detector here, so we can reconstruct different types of tracks. For example, velo tracks that have hits only on the velo, which is our tracking subdetector around the PP collisions. Then we can have velo UT tracks, which we call also upstream tracks, so that have hits on velo and UT. The upstream tracker is our tracker just before the magnet. The magnet is a dipole magnet, so it bends track in the XT plane. So if we look like this, it bends track, let's say, left and right. and then we have a sci-fi tracker after the magnet, which is scintillating fibers, and this is to reconstruct what we call long tracks, which have hits on velo, UT, and sci-fi. And we have also other different type of tracks. For example, downstream tracks that have hits on UT and sci-fi, and T tracks, which have hits only on the sci-fi. And about this in HLT1, there's going to be brief talk talking about this later this morning. And okay, so I will explain to you how the HLT1 tracking sequence works. This is inside Allen. So we start with the reading and decoding information from the tracking subdetectors, and then we start with our reconstruction. So from the velo, tracking and vertexing, and then tracking using the UT and sci-fi, and then we can fit our tracks and find secondary vertices, and we can use also some information from particle identification subdetectors, so having information from muons and calorimeters for electrons. But at the end, the goal of a trigger is to select events and proceed with the LHCb data flow. But okay, let me start talking about tracking, and I want you to follow this little sketch here on the bottom left. So let's start with the velo. So the velo is composed of 26 silicon pixel modules, providing a spatial resolution of around 5 microns. And in practice here, there's no magnetic field, so we have straight lines. And so this is also very crucial to find primary vertices. And the idea for this algorithm is to have our hits and sort them by phi, which is the angle, the arctan between x and y. So when we sort this, then we can do a search by triplet, and the search by triplet works like this. So this is 3 subsequent modules. We find a hit in the middle, and we try to look for the 2 hits in the layer before and after. So this is how we build our triplets. And to show you the sequence of velo tracking, we create the triplets given 3 modules like this, and then we try to forward the triplet to the next layers. And then we repeat this search looking for the other triplets and extrapolating them again. And with this method, we have a reconstruction efficiency of 99% of the track of interest for LHCb, which is really nice and really important. So then we can use the velo tracks as I told you to find primary vertices. So what we do is we extrapolate these velo tracks to the point of closest approach to the beamline, and we try to find primary vertices. So this is how we extrapolate them, and this is we see Z in this axis, and we try to find clusters and fit our primary vertices. And I'm showing here on the right efficiency versus number of tracks in the primary vertex. Of course, we're more efficient in finding primary vertices if we have more tracks pointing to that primary vertex. And okay, so let's continue following the sketch. We have velo tracks. We can extrapolate them to the upstream tracker. The upstream tracker is composed of 4 layers. So here, just showing two lines, but it's two layers per station. So it's four layers of silicon strips. And so in practice, what we do is we extrapolate our velo track, considering that here already we have some residual magnetic field, so the track is bending a bit. And we parallelize the tracklet finding using search windows and finding. And we require tracklets to have at least three hits out of 4. So I don't want to go into too many details of how the algorithm works. What I want to say is that here the goal is to reconstruct tracks that either have low momentum, so they do velo sci-fi, and then by the magnet they bend out of the acceptance, or also long tracks, so that they do velo UT sci-fi. Here already, because we have some magnetic field, this provides already a first momentum estimate, and this really helps reducing the number of combinatorics that we have to check when we have the full long track reconstruction. And this is how our efficiency looks versus transverse momentum, reaching around 90–95% for tracks over 1 GeV of transverse momentum. And then continuing following our little sketch, velo UT, the magnet sci-fi. So here the sci-fi is composed of 3 T station and 12 layers of scintillating fibers, so 4 layers per T station. So what we do, we extrapolate our velo UT track using some B fields parameterization, trajectory, and we extrapolate to the sci-fi. We open search windows based on the first velo UT momentum estimate that I just discussed before. And what we do is we do a search by triplets. So for example, here I'm showing that we can build triplets using the first layer in each of the T station. We build our triplet, and then we try to extend the track using the other layers, and we require 9 hits minimum out of 12. And okay, so the goal here is to reconstruct tracks with momentum greater than 3 GeV and no PT requirement. And if we look at the usual efficiency versus transverse momentum, we see that already at 1 GeV, the efficiency plateaus around 90%. And what is really important here is that we want a momentum estimate from these tracks. And I'm showing here the momentum resolution versus momentum, and it's around 1%, which is actually our goal in LHCb. And then actually on the next slide, I have reconstructing long tracks without using the UT, because as we also saw in the last presentation the other days, the UT will not be available at the beginning of the data taking. It will be available from December on. So we need to be able to reconstruct tracks without using information from the UT. And in practice, not having the UT means not having a first momentum estimate and not knowing the charge of the particle. So the idea here is to have our velo track and extrapolating as a straight line to the sci-fi. And here we assume a minimum momentum. So momentum greater than 5 GeV and PT greater than 1 GeV to decide how big is our search window. And we don't know the charge. So let's say we don't know if it's bending left or right. So we open double-sided search windows, and then the algorithm is pretty similar to what I explained to you before. So a triplet search, and then we extend to the other layers. And here, so the algorithm is focused on this higher momentum tracks. So momentum greater than 5 GeV and PT greater than 1 GeV. And we obtain very similar physics performance as having the UT for this higher momentum tracks. So we see here the comparison of with UT and no UT still efficiency versus transverse momentum. But of course, we increase the ghost rate. So here I'm showing ghost rate versus PT with UT, no UT. With UT, we are more around 2–3%, while with no UT, we're around 7–8%. Which understand why the UT is so useful for us. And all this keeping the throughput comparable. But I want to talk about the throughput later. I want to finish about tracking. The last step is doing a Kalman fit that improves the estimate of the track impact parameter, momentum, and helps to reduce some ghost. And for Allen in HLT1, we need to be fast. And so three Kalman filter versions were developed, a full detector parameterized version of the extrapolator, and then a simplified with some with some assumption, and then also a velo-only parameterization. So using then the momentum from the forward tracking, and I'm showing here on the left, for example, this is the impact parameter resolution versus momentum, and we see that it's quite similar using this tree version, which is I mean the impact parameter is an important variable for LHCb. So we use the version, I mean the default version is we use the fastest, which is this velo-only parameterization, but of course it can be switched in the future. And so I talked about tracking, but I want to talk a bit also about particle identification. So what we can use information from the muon stations. So in practice, what we do is we have our long tracks, and we can extrapolate them to the muon station. And with forward tracks with minimum momentum of 3 GeV, we can see of hits, matching hits in the muon station. And this is very, very important to do selection of decays that has muons in the final state. And here I'm showing some efficiency of the muon and the efficiency versus momentum. Then we can also use calorimeter information, and this is actually a first in HLT1, and this is used for electron identification. So here the idea is quite similar. We extrapolate our tracks to the calorimeter. We look for matching cells in the calorimeter, and this is our electron identification. We can also do some Bremsstrahlung reconstruction to correct the momentum. Just to explain you how the Bremsstrahlung reconstruction works. So we have an electron and we have our magnet. So if the electron emits a Bremsstrahlung photon before the magnet, the photon will just go straight into the calorimeter, while the electron will bend in the magnet and maybe finish in a different position in the calorimeter. So we can look at clusters here, look for the energy, and add it back to the electron to correct our momentum. And then there is also some work ongoing on clustering and neutral reconstruction. So I talked a lot about tracking, but what is really important in HLT1 is, of course, throughput. And here I'm showing the HLT1 throughput measurement for different GPU cards using a sequence with UT and no UT, just to show you also the comparison. And in LHCb was chosen the RTX A5000 GPU as default. So okay, let's look together here. The throughput, if we look at the A5000, we are around 170 kilohertz. So we said that we need to take data at 40 megahertz. So we need around 150 to 100 GPUs to take care of this. And LHCb has 500 available slots. So this is also very promising for the future. And one of my final slide, at the end, the goal of the trigger is to do selection, so to select events, and this can be done because LHCb needs to fulfill a broad range of decay of interest inside LHCb. I'm showing here a list of HLT1. It's not complete, this list, but it's just to give you an idea of the kind of lines that select event that we have. And what is important that I want to say here is that this has a good scalability, in the meaning that if we reach 100 HLT1 lines, for example, this has only a few percent throughput lost in the throughput. And of course, once we have all our lines, we need to tune to have a 1 megahertz output for then going into the buffer, align, and then go to HLT2. And we have selection lines for physics, but also for alignment and monitoring purposes. Okay, so well, I reached my conclusion. So what I want to say is that LHCb is ready to face run 3 with 5 times higher luminosity and having a full software trigger that takes data at 40 megahertz. And we're really looking forward to see the first track reconstruction with our first collision in the next months. And then I discussed that GPUs are optimal for the first high-level triggers task, because tracking is a highly parallelizable task and very flexible for different physics use case of LHCb. We have also some available PID information, particle identification information inside HLT1 from the muon station and the calorimeter. And what is, of course, really important is throughput. So with around 200 GPUs, we can take care of the 40 megahertz input rate of LHC. LHCb has 500 available slots. And also I discussed that when we will increase the luminosity, maybe in the high Lumi upgrade, this can be handled by Allen just in improving the GPU technology with no saturation expected. And so this is all very, very promising also for the future. So thank you very much, and this is my conclusion.
Thank you, Alessandro, for bringing us back on time already on the first talk. I do not see any questions on the chat, nor I see any hands. So let's start with the room. Any questions here? Bob, looks like you.
So my question is, what is the fundamental difference between the HLT1 and HLT2?
So
the sense of algorithm or question.
Okay, so in practice, in HLT1, we deal with the 40 megahertz. So we need to be really fast, and we don't reconstruct all type of tracks. We need to select events, and we need to go from 40 megahertz to 1 megahertz, and then we can send this 1 megahertz to HLT2. And in HLT2, we have way more time, so we can reconstruct more different type of tracks, and we can also use, for example, particle identification information and everything. So let's say we called it partial reconstruction and full reconstruction. This is, let's say, the difference between.
Okay, so and going back to the throughput chart.
Yes.
Is UT and no UT.
Yes.
So what is the advantage of using the no UT? I mean, it looks almost the same between them.
Yes. So in practice, what we do with no UT, because the UT really helps tracking. We reconstruct higher momentum tracks, as I showed you. You know, when I showed you the no UT, we focus on higher momentum tracks. So with momentum greater than 5 GeV and PT greater than 1 GeV. So we reconstruct less tracks than what we do with UT. So then we can keep the throughput comparable. I mean, at the end, what we care is to have the same throughput, because we need to take data at that rate. Then, of course, we can reconstruct less tracks because we have less information. We don't have the UT, but this is what we do.
Okay.
Any more?
Yes.
Yes, go on.
Alessandro, do you after you found the track with the momentum estimate, you revisit the straight line estimate with in the fit with the proper momentum estimate, right?
Yes. Yes.
For enhancing the impact parameter
Yes.
resolution. Okay.
Yes.
Yeah.
This is our quickest approach, because at the end we need to be fast in HLT.
But then do you do a forward backward fit or a back seated
So
common field fit?
So yes, it's done on the velo track backward using the information.
Using the momentum estimate
using
from
the momentum
okay,
estimate
yeah.
from the long track.
Right,
So
right,
it's done
right.
after.
Yeah, okay. I get it.
You described how you do some calo matching to recover Bremsstrahlung energy loss. How often do you get accidental coincidences for calorimeter clusters that didn't actually come from some photon from the Bremsstrahlung?
So I don't think I have the exact number. What I can tell you is that 50% of our we can reconstruct correctly the Bremsstrahlung photon from 50% of the electrons we have before for the magnet.
Okay.
Then, of course, if you are after the magnet, the photon will be exactly in the same cluster, in the same position in the calorimeter.
We actually have time for more questions, but what is that? So I guess that's a technical question more than an algorithm. So when you run through your algorithm, do you have a cross event boundaries, or do you process always one event at a time? So you do all of your process, all of your reconstruction one event at a time, or do you accumulate tracks over multiple events and send them to the GPU all in one go, for example?
Yes, this is what we do. So what we do in practice is we have our event builders. I think I showed you at the beginning, no? So we have the event builder is in practice CPU servers, and we build event packets. And once we have an event packet, we send it to the GPU and we parallelize over events. So each event gets one block.
Okay, but each event has its own block and
Yes.
does its own thing. Okay. Thank you. Let me see. Well, let me ask anyone on Zoom? Any questions from Zoom? Doesn't look like it. So let's thank Alessandro again.